Okay, so we'll start by like just an administrative minute here. The QCOF conference is coming up. It's going to be from July 20th to 23rd, and we're going to have a special day on the 24th just for this effort, for the openQSE effort. It's going to be on the 24th, so this is an open invitation to everyone who would like to make it. Once the registration opens, I'll send out the link. Be prompt because Oak Ridge you'll have to, get a pass and all this nice stuff, so it might take a little bit of time. And this will actually launch the 4 working groups that we talked about before, officially launch it. So it's going to be basically divided into 4 concurrent sort of tracks, each one focusing on a specific work group. The other thing is we have a Confluence instance. If anybody is not on it, please send me a text and I'll add you. So there's a few ongoing efforts, and the idea is to create like milestones that drive this initiative forward. So we have the architecture SC paper that we'll discuss quickly today. That's almost completed. We want to expand this into a bigger journal article. And the purpose of this is to like dive into each stack that was discussed and expand on it and write out the details, and from there we can get more like fine tune our architecture. There's also another paper that's being worked on right now. It's a system integration paper. It's basically looking at how those quantum resources are going to fit in data centers. This is led by Johannes, and we have a weekly meeting that's going on. So if anybody's interested, let us know, and we'll add you to that. And there's also a compiler survey paper that's going to get kicked off at some point. It's led by Josh and Gwen. I'll give it over to Josh to talk about it quickly.
Yeah, hey folks. Mainly what we're going to do is we're starting out by just doing the survey to kind of gather like one feedback, hear what people's thoughts are. And what I would ask is why don't we put a deadline on like say the next couple of weeks? Maybe we'll do 3 weeks so that way we can do time zones. And then the goal is Gwen and I can get that kicked off probably starting later this month. Definitely into early May is our thinking.
Cool. So we'll send out this in an email, the link to in an email so that everybody has it. There's also a QRMI QDMI alignment effort. So IBM started sent out an invitation. So we'll work together to kind of include people that might be interested in this, if that's okay. And that I think will kick off next quarter. All right, so this is for the current ongoing efforts. We have upcoming speakers. So on April 13th, that's next week, Quantinuum will talk about their approach to HPC integration. And then the Indian Institute of Science is going to talk about application patterns. It's a presentation that they put together. We are looking for speakers, so we want to cover different types of topic like control electronics research, energy efficiency, compiler, deep dive, system integration. All these topics I think are pertinent to the software stack that we're discussing because they impose different types of requirements. So the more we understand, the better we design the system. We're going to soon transition to the weekly meetings are going to transition to more like the speaker roles that we have, but also working group report backs. So things like today to gather feedback and get people's input on the design. There's a couple of upcoming events. QCE 26 is coming up and SC 26, and in SC 26 we already have an IBM and Oracle workshops accepted. openQSE has like a slot in the Oracle workshop, so we'll give you more details once we have that. So any questions there? Cool, perfect. So moving on, what I'll do is this thing turns. Okay, here we go. So this is like the phased approach we kind of discussed earlier. Right now, the effort that we're undergoing right now is basically to handle these two, identify and organize the software layers and define the software component categories. So this is the purpose of the paper in a sense. We want to try to look at all the stacks that are out there, find the commonalities between them, and sort of derive a general architecture that would fit what everybody's doing. So here, what I'll do is just kind of step quickly through the different phases of the paper or the different sections of the paper so that everybody gets like a good idea of how the paper is structured. We'll share it afterwards, but just so that everybody's aware of what the paper talks about. So what we did is we defined 4 classification axes. So we said all papers, all the stacks will have to satisfy requirements from sort of different sources, 4 different sources. There is the deployment model, so the stacks have to support run in the cloud, run on-prem or in federated models. We said that there's multiple hardware modalities. There's superconducting, ion trap, neutral atom. So the stack has to support all these different modalities. And we talked about application interaction patterns. So we identified like 2 high-level workflows, interaction patterns. One is called workflow and the other is called accelerator-centric. I'll get into that a little bit later. We said that the stacks have to support these type of patterns, and we talked about NISC and FTQC, and we said, like even if the stack is currently NISC, there has to be some path toward FTQC, and the design has to support that. Again, for the people that joined in this, please feel free to jump in if there's details that you want to add. For the deployment model, we talked about 3 different deployment models. We talked about the cloud. We talked about on-prem, which would look like Site A. And we talked about federated, which the idea is you have a Site B that might contain only HPC and quantum resources actually in Site A, and then you need to have like Site B applications running and Site B running using the quantum resource in Site A. So that's the federated. The federated looks like cloud bursting in a sense, because as Site B would use the quantum resource in Site A, it can also use some quantum resource in the cloud. So there isn't much difference between a federated model and a cloud bursting model, so to speak. For the quantum hardware modality, we talked about how the different modalities differentiate or have different like latencies and control and orchestration constraints. Superconducting, for example, can be very short, while maybe ion traps might be a little bit longer. And that introduces different requirements that the software stack has to handle. Then we talked about the application interaction patterns. So we identified 2 patterns, like 2 high-level patterns. One is the workflow centric, which is the picture on the left, I guess, here. In this case, you have a resource manager, and then that can either reserve the HPC. Sorry, I'm missing this. No, this. Okay, so the resource manager, and you have a workflow manager. Sorry, maybe it's not in this picture. The workflow manager, basically, you describe your application in a workflow diagram that separates the classical steps from the quantum steps. The classical steps, like pre-processing steps, would execute on the HPC. The classical steps would, then the results from the classical steps are absorbed by the workflow manager, and then those are allocated, then the quantum resource is allocated and they run the quantum steps and then post-processing after that. The idea is at any point in time, the HPC and the quantum are not really interacting with each other except through the workflow manager, which collects the results and launches the next step. The accelerator centric is a different workflow, which is more like a GPU execution model. You can define your kernels, and then during your larger application, you can launch that kernel as you would a GPU kernel that would execute within the lifetime of the application. The results will come back, and then the classical program, which could be like a simulation campaign, for example, would get those results and use them. So the constraint with the accelerator model is that the quantum kernel is expected to complete within the runtime of the hybrid application, while in the workflow case, you might not need, there isn't that coupling really because you're separating the classical and the quantum steps. This is not talking about QEC because QEC is a separate like case here. Lots of people are of the idea that workflow as you transition towards fault tolerance, the quantum runs are going to be really long, and therefore the workflow model might be more more likely to be used for these for the fault tolerant era because you're going to have really long running circuits, and then you wouldn't want to keep the HPC allocated while the quantum is finishing up. So quickly, there is a few design patterns, like for example, you can run a deep circuit and get the results, or you can have an ensemble of shallow or deep circuits you run that are independent of each other and you get results. You can have the iterative optimization loop where you run a circuit, get results that optimizes the next circuit and so on. And then, for example, there's other resource usage. You can have multiple QC resources, which is not really because quantum resources are scarce right now. This is not practical, but it could be in the future where you can assign a job, one quantum resource, and then it can use that, or you can have one quantum resource that all the jobs share. So all these impose requirements on the software stack that need to be fulfilled. And the quantum computing era, I'm not going to spend too much time on that. The idea is you want to do support FTQC. And there are lots of the stacks are going towards that anyway. IBM, IonQ, all the vendors are pretty much working on the fault tolerant side of things. So their stacks are going to support that. And we need to see how that support is going to percolate up the layers of the software stack. So the stacks that we examined in the paper were IBM, MQSS, JHPC from Japan, Pascal, QB, AWS, Xanadu, and IonQ. I ordered them in the order that they were presented in this series. From all those different stacks, examining those stacks, we identified the general workflow. The idea is you have a classical compute that could be on-prem or some laptop or whatever, like something out of the a laptop outside outside the security zone of the quantum resource, or it could be within the security zone of the quantum resource that submits a hybrid job. We want to have some sort of job submission abstraction so that we don't re-implement the way we describe quantum resources. And then that goes through the resource management that can actually allocate both the classical compute or the quantum resource, or it can only allocate the quantum resource because it's expected that the quantum resource is going to have some classical support there that can run those scripts directly on the quantum resource. So you might not need explicit classical resources allocated. So this is the workflow that is expected to be used for all the different, or that is supported by the different stacks. So out of the different stacks, what we found is there is a set of design patterns that we talk about in the paper. There is layered, all the stacks basically have a layered architecture that's just good software engineering that separates the application, runtime, compilation, hardware. All the stacks have this idea of a stable upper interface that doesn't change, that uses the SDK that they provide, and then anything near the device is abstracted by the back end. You have the idea of progressive lowering. So you have some sort of a compiler abstraction or compiler tool pipeline that takes the circuit and lowers it all the way down to the hardware. you have some sort of integration into the scheduling that varies from stack to stack, but most of the stacks have this reservation, whether it's within the cloud or they use something like QRMI, QDMI, which we'll talk about in a little bit. Most of the stacks also build, have built-in telemetry, so they all collect some sort of data from the system, whether execution state or like system health or debugging information, and but it's represented in like each stack represents it differently, and all of them support hybrid workflows. So one of the things that, sorry, I meant to change this to future features that we can implement. One of the, so looking at all this is all good, but there is some we decided that there could be some opportunity to improve on the state of the practice. We might want some common runtime API to decouple the SDKs of the application from the runtime API. So instead of everyone implementing their own backend and each backend is different from Qiskit to Penny to other packages, we might have a common runtime API. We also thought that it's a good idea to have a composable compilation. So all stacks have that, but maybe they're not compatible. So maybe you can look at a way to make the different compilation pipelines compatible. We want to have right now, all the connection management and the transport management is offloaded to the back end. So the back end developer is expected to write all this. So there could be some repetition there. We might think about some abstraction that also includes like RPC implementation or encryption or other things that can happen during transport. Most of the used communication patterns right now that is supported is unidirectional. So when you submit a request to the resource, you're usually saying, okay, send execute that circuit or collect those results. So it's all one directional. The runtime sends a request to the quantum side to ask for services. But you can think in the future that there might be the opposite direction as well. So the quantum side can request other services from higher level APIs. Like, for example, if there's a compilation step that can take a long time that the quantum resource has to accomplish, maybe it wants to allocate on-demand resources to do this compilation step. So there is a bidirectional communication pattern that needs to be supported. We also thought that multi-tenancy might be a good thing to think about. Lots of the vendors already do that. For example, when we have a cloud service that had you submit many requests to it, what happens internally is it schedules those requests and on the resource based on some criteria, whether it's like a customer tier or how long the circuit is. So there might be some opportunity to unify this a little bit. What else? Structure. Anyway, I think that's good enough here. So these are the future direction that we might look into when we design like a common architecture. We created this table. We're still working on trying to refine it. The idea here is to just sort of have the different layers that need to be implemented that we just talked about right now, and show what the stacks are doing. And you can see once you start looking at this table, you can see that lots of the stacks are starting to use common things like QRMI and QDMI, for example. Lots of the stacks are using these. So this is a good opportunity to start looking at those interfaces and maybe formalizing them a little bit more. And finally, we come to the, I don't know why it's so greeny. We come to the HPC, the resource, the architecture that we are proposing. I'm going to speak about it a little bit, and then I'll open it up for discussions afterwards. So the idea is it's divided into 4 components here. You have the HPC control node. You can have a quantum resource. You can have a quantum access node or nodes. and you have the HPC classical compute or HPC compute nodes or the classical compute nodes. The idea here is you don't have to have all of them at the same time. You'll see, for example, the quantum access nodes and the classical nodes look very similar. Like what runs on them is very similar. You can run the hybrid application on the classical node, or you can run it on the quantum access node. So for example, say some external user wants to submit a script to run, they can use that quantum access node to run their application, and then the access node is used. Or your application can run on your compute node that you reserved, and then it submits the compiled quantum task in an intermediate representation to the quantum resource for execution. So the idea here is to just show that the architecture we propose is composable. You have the hybrid application which runs. The hybrid application is abstracted, or the details of the software stack is abstracted by a runtime interface. So think HIP type of interface where it underneath that interface, then you can implement the you can implement it differently. Then you'll have a tool/compiler pipeline infrastructure that takes the quantum task that needs to run, and it can apply some transformation on it, and you can progressively lower it. So the reason you have it, for example, on the classical compute node, on the access node, and on the quantum resources, because you can do different levels of lowering on each compute element. So on the classical compute nodes, you can do a high level transformation, and then once you get to the quantum resource, then you can lower it all the way down to the hardware. You can also have some program scheduling. Like we said, that on the quantum resource, you can submit multiple quantum tasks, and you need to schedule those on the QPU. So if you think of the QPU right now, the versions that we have, at least, you can think of them as single core processors. So you just have one process that runs at a time. So same thing here, you can have one circuit that runs at a time, but if the circuit requests like a million shots, for example, you can subdivide those shots, and you can try to switch between different jobs that are running. So this is the idea of scheduling multi-tenancy in this context here. We also thought as you move towards fault tolerance, you will need like a fault-tolerant execution engine that's tightly coupled with the control electrons and the QPU that does the actual quantum error correction within the time limit of the QPU. But then some other level, like what IBM talked about in their paper, for example, the hierarchical quantum error correction that can be offloaded to the logical control layer, which can do some level of error correction. Or you can think of cases where you can have a quantum, like a big circuit that maybe is compiled incrementally, and that the incremental compiling is not really doesn't really need to meet the very like the deterministic time deadline or the time domains of the QEC. So that can be offloaded to a higher level, which can do that. And as long as you feed the instructions down to the control electronics such that it doesn't starve, you can do some incremental compiling there. You can also have the idea of a capability layer, which like discovers the capabilities of the underlying hardware. The idea here came from smart NICs and other devices that we use right now. With smart NICs, you can have for example, can support specific features in the hardware like tag matching, and then this can be discovered by the higher level software in order to be able to use this capability that's in the hardware. So not all hardware will have the same levels of features embedded in them, so that's why a capability layer is useful. So basically, that's what I had. I flew through it quickly, but I wanted to keep time for people to digest the architecture and suggest ideas that we might not have thought about. So kind of open it up for discussion now.
Amir, in the table, how is the runtime interface defined?
Yeah.
Because it seems like there's kind of a mix of things um, in the runtime interfaces table. Like there's, for example, Continuum has QRI, whereas other people like IBM put in there's QRMI there. Now, are we talking about, and then the other things about the SDKs are more like front end interfaces, right? So are we talking about different levels of runtime interfaces or one level of runtime interface?
The idea, so if we go back to this, what I
Uh-huh.
was thinking about is two levels of runtime interface. There is the application facing runtime interface, and then
Okay.
there is the hardware facing interface. The hardware facing interface is like the QRMI, QDMI. You get a task, you execute it on the hardware, you get some result back. But at the application level, again, not like looking into the future, you might have, for example, you might be dealing with multiple quantum resources. So how do you deal with multiple quantum resources at the application? Does the application now have to take care of each quantum resource, or are they going to be abstracted under a specific uh, under a layer which abstracts away the like how the system deals with the job submissions to the multiple resources. For example, if you have like three IBM machines that are identical, you can have them as part of a group, and then when you submit, when the hybrid application says run a circuit, it doesn't care which machine it runs it on. But if you don't have that, then all three have to be exposed to the application, and then the application has to decide which one it runs on. Now, I understand there is a case where, like, there's an argument for saying right now, the machines are so delicate and they drift over time, and if you want to, like squeeze all the performance out of it, you really need to understand the hardware or what the state of the machine is at any point in time. The application has to do that, but I'm hoping as time goes by that requirement is going to not be as prominent. So having some interface that abstracts that away might be good.
Okay. Okay. Thanks for the clarification. Okay. So in that case, then it seems to me like so in IBM we have cloud. I think in IonQ we have cloud. I guess those are kind of out of place then, right? Because those are higher level interfaces. Josh, what do you think? Because I think you're IonQ, right?
I'm sorry, I didn't hear the second half of your question. You mind repeating it?
So I'm wondering if so now that Amir clarified what he meant by runtime interfaces, right, which is
Uh-huh.
between the SDK and the lower layers, but also just above the hardware. It seems like putting IBM Quantum Platform and Cloud API in your row, the IonQ row, seems a bit out of place.
In what sense? Like in terms of like how you access the resource or the runtime interface is what you mean?
Yeah, those seem like a higher level interface to me rather than the SDK interfaces, where you're generating IR and things like that, and then the lower level QRMI, QDMI, right, where you're accessing hardware resources.
Yeah, and I think in IonQ's case in particular, we do have emerging support for it at lower level for certain customer sets. I don't think it's general availability, but like it is something that we are looking to add. And I'm just trying to remember if we've had precedent for running it today. But
Okay.
I do see your point of that kind of like, I think what you're getting at is that the majority of our jobs and applications you have to access through our cloud front end, for lack of a better word, right? Is what you're getting at.
Yeah.
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 Um, and sorry, which one was it specifically? Was it the resource interface or the runtime interface you were kind of
Runtime
thinking?
interface. Yeah, runtime interface.
Yeah, and I think it's we technically can ingest it. So like there is no problem with our systems ingesting it. I think it's just that's not typically the preferred way we do it, if that makes sense. So like technically we
Hmm,
can do it. It's just not the preferred path that we do pass them around.
I see. Okay.
When you say pass them around, what do you mean by that, Josh?
When I say if you did pass it in the S, so no matter what, they all end up in the same spot. So like we have several entry points into our system, but at the end of the day, they're ultimately on the back end still all going to the same place before they get translated to our intermediate representation down the chain. So even when we do receive something, we do still transpile it into our intermediate representation. That said, I think we can optimize performance there. Like that's an area we're looking at maybe doing some gains down the road. But like we do ultimately still pass it through our transpiler just to get everything kind of sanitized, I guess, for lack of a better word.
Mm.
So with that said, like love feedback if you think maybe we need to update the row on the table. Like totally open to that if you think that with the way I described it, if that would maybe be room for improvement, how we have it documented here.
So one, just to be fair, there was an earlier version of this where we had the runtime and resource interfaces in the same column and we didn't separate them. And I think that maybe that's my fault. Maybe that's causing a little bit of confusion because right now there isn't like all the stacks rely on the back end as their entry point into the whatever they want to execute, right? So you have an SDK that forms a circuit, then it calls backend.run on that circuit. And then the backend.run then reduces that down to, or lowers it down for something that it can execute afterwards.
Yeah, and that's what I'm just having to remember. Apologies, I'm having to pull up the paper because we use just slightly different terminology internally. So I'm looking how precisely in the paper we define runtime and resource interface as we're talking.
Mm.
So the other thing that's not clear in the table, which would be nice to get some feedback on, is that last column here, right? Does it make sense? Because everybody, all the vendors are working towards some fault tolerant support. Does it make sense to keep it in there? The only exceptions would be like the stacks that are not produced by vendors like GHBCQ and MQSS, for example. They plan to support fault tolerance once it's there, so they manage the fault tolerance rather than implement the error correction itself. So I'm not 100% sure if this last column is clear or not. So I'm open to suggestions on how to solve that.
So is there any difference between the noisy quantum computer and the FTQC architecture? Yes, in our reference paper, we show some differences, but in this paper, maybe most of the interface should be the same. Is it correct?
Fair is this one doesn't really show interfaces, but it does have this fault tolerant execution engine layer and the logical control layer, which maps towards the hierarchical decoding and the IBM architecture. So there is some difference.
Yeah.
But I'm not sure exactly how to say the stacks right now. Obviously, everybody's working towards FTQC, but like, do we just say in this table, like we added this actually here, we said as of April 2026. So if we say as of April 2026, should we just say at this point, none of the stacks support FTQC or just remove it completely? I don't know if that's the right thing to do or not.
I would kind of lean towards, I mean, I think my proposal would be maybe drop it because just like what I would say is like, I don't think any vendor, like every vendor is working towards FTQC. Like, I mean, I think maybe we add a sentence that every vendor is working towards it, just throwing that idea out there.
Neil, go ahead.
Yeah, I'd probably agree with Josh. I think like within our stack, like we're building and we have, we've had a couple papers about QED and QEC codes on our newest computers, but like the way in which it's implemented is like I think not a automatic thing that you get. And it feels like maybe that's kind of the idea here is something where it's like it's fault tolerant without the circuit itself is kind of like unaware of fault tolerance. where I think like current state of the art is more like the circuit is, custom crafted by our, QEC researchers to actually, achieve, whatever the surface code or GoTo code that we're running. But I think it's probably kind of a distraction, I think, for this table.
What do you guys think? Is that generally, because also, okay, to be fair, just to kind of go back to the older version, I think we had here the exposing of the control electronics behavior, like which stacks expose the control electronics. That's why for IonQ, for example, you have this microcode RPU and timing exposed, because as far as I understand, within the IonQ cloud, they expose some timing information that can be ingested by the scheduler to make some scheduling decisions. But that's within the IonQ, internal stack, right? And I'm just not sure if it makes sense to go into that level of details in this table or not. So that row serves two purposes: the FTQC and the control electronics. So that adds to the confusion, I think.
Yeah, and I think. Oh, sorry. Go ahead, Neil.
Oh, yeah, I was just going to suggest, Amir. I mean, it seems like there's not much boldness, and I mean literally like bolding things in that column, which feels like maybe it's kind of like in some ways like not the right data for this. I feel like the rest of these columns could have some interesting kind of like stuff in common, but that one doesn't really expose so much as commonality across stacks. So yeah, it feels like it's maybe orthogonal. Yeah.
Yeah, and I was gonna agree that and I also just like kind of what I'm thinking is especially on IonQ is like is the fact we're presenting that novel, and I would kind of lean towards no. So like that's why I'm inclined to say like maybe I don't think it's novel the fact that we're like exposing that timing information, just thinking out loud. So that's kind of why I lean towards maybe just dropping that column altogether. That said, when we do our bigger paper, I think totally we could dive in and talk about this stuff in more detail. But I would say for this higher level one, I would propose dropping that column.
Yeah, I think that makes sense. Anybody else has any opposing or concurring opinions? Okay. So going back to the runtime interfaces and the resource interfaces, it's still confusing. Back to Yunho's point.
I got an answer there. Sorry, I missed what Yunho was saying. Yes, the left column should only say QRMI and Cloud API, and then the right column resource interface should say QDMI. So I fixed it and pushed the change up there on IonQ0.
Oh, okay.
I think that was just a copy paste error.
Does that solve the problem that you were thinking about, Yunho?
Yeah, I think so. But then in the Pascal column or the Pascal row, I don't know if Alex is on. We have QRMI in both runtime and resource interface. So I guess they are using QRMI as a resource manager. Yeah. Yeah, but it seems a little strange having it in two places.
Well, technically,
same with
QRMI,
IBM. Yeah.
Sorry. Yeah, QRMI, I think, has the two sets of APIs. It has the resource management APIs, like to reserve the resource and do authentication, etc. But it also has the, run type interfaces or run circuit interfaces. So like run circuit, collect results type of interfaces. So it is used on both sides. It's used to reserve the resource and it's used to run the interface. Same with QDMI. I think they have the same categories of APIs there. So maybe it's worth, like in the QRMI and QDMI sections, it might be worth just explaining that.
Yeah, make sure that distinction comes out. Yeah, okay.
So what does multi SDK support mean? So can we list or more specifically?
Sorry, I missed that. Hiroshi, can you say again?
Yes, JHPC runtime and openQSE things, yes, it supports the runtime interfaces, or multi SDK support, but can we list, more specifically about what is SDK will be are supported or?
So to be fair, I think the IBM stack supports multi SDK as well. I think that was part of your, if I go back to where's here? Like it can, here you have other SDKs, right? So you
Yeah,
can
true.
generally have like either a Qiskit program or other SDKs running, and then those SDKs just use the QRMI and they translate, I guess, to whatever intermediate representation the quantum vendor expects, right?
That's true. And also,
So
yes, maybe, yes, other SDK can access our APIs, like, CUDA-Q can access to my
right,
system as well.
yeah,
So,
might be worth adding that in here as well.
yeah, and yes, CUDA-Q is, vendor agnostic, I guess, and then, Qiskit is also, and then I'm confused, still be confused, yeah, Qiskit is here, or Qiskit is yeah.
Sorry, I'm not following. Can you say again?
Yeah, Qiskit, or suppose, yes, or maybe there are most of the backends, and I don't know, I'm still thinking, yes.
So we can keep it generic. We can say like multi SDK for the stacks that support multi SDK. But to be fair, that's another confusing part because everybody they can use multi SDK and then they can
Right,
convert into openQASM or something, and then they submit the openQASM to the IonQ or Pascal
right.
or anything, and then that gets translated or like compiled down to the whatever hardware um, representation is required.
And that's exactly kind of what we're doing. I mean, it's like that's how we run our cloud front end. Is it just it's anything to what we need for our systems. So effectively.
So does it make sense to, I don't know, I'm thinking off the cuff right now. Does it make sense to change the runtime interfaces to say intermediate representation and then just, wow, that's gonna, no, never mind. Bad idea. I'm open for ideas. I'm not sure what's the best thing to do here. Neil, sorry, you had your hand up. Sorry, I apologize.
No, it's actually good because I had a bit of a slightly adjusted topic, but I was gonna say there's like maybe a few adjustments I'd make to the continuum row. Can I like just ping you those or uh we don't need to like talk about it. It's not like that interesting, but just for the sake of accuracy. Yeah.
Yeah, sure, no problem. Okay. Can I bug you then to think if those changes that you're thinking about, like, do the rows make sense to you, or do you have any other ideas on how to differentiate the rows?
Well, yeah, I think we have like there's a little bit more for us. Our compiler toolchain is actually quite deep. The Guppy and ticket side is actually kind of like that's pretty early on, and then there's like actually a lot of like other stuff subsequent to that, if that makes sense. Because the same as with all the placement routing we have to do, there's like a lot of internal effort required for those types of compilation. Uh, I think otherwise, I might suggest that we try to differentiate runtime and like cloud interfaces or external APIs. Because like for us, like Nexus is like, it's our external API for, general usage and everything, but I feel like it's kind of like irrelevant or it's orthogonal to this use case in some ways. Or at least like compared to like talking about like QDMI and stuff where we're like really talking about like a tight, specific runtime API. It's kind of like more like just an informational, like maybe the way you drive that stuff later. So maybe there's a column that we'd separate out like IonQ's API and AWS and IBM Quantum Platform and And honestly, I don't know the rest of them well enough to pull out the cloud part. I don't know if that would be useful.
Any thoughts on that? Yeah, I'm gonna write that down so I don't forget it. So the idea is to separate, like instead of have a, or beside the runtime interfaces, have a cloud interface, and then on that you would have the cloud APIs that the specific stacks support.
Yeah, and I don't know if there's actually that much necessarily in common for that, but it might be just an interesting way to separate out some information. But it doesn't sound like there's a lot of excitement from the from the crowd. So.
Are you proposing, Neil, to like drop that column into a table on its own?
You mean drop the runtime interfaces column?
Yeah, like I guess what I'm like, are you thinking like put it in a new table or like maybe modify the existing table? Like what were you kind of thinking?
Oh, I was thinking just another column in this table.
Got it.
And so the runtime interfaces column will probably get like a little bit skinnier, and then some of it will move out into that column.
Yeah, my thinking face, I just was going to say, is like building on what you're saying there, Neil. What was resonating is it's just kind of like that part is so diverse across the vendors. That's what my thinking face is trying to think, how do we best render that, you know?
Mm-hmm. Mm-hmm. It might, however, make the runtime interfaces column look more unified. So they kind of like accomplish maybe the task of that a little bit by removing something that's kind of different in all of them.
So just to kind of make the idea more concrete, let's say you have that cloud column, what would move into it? Like the SDKs would be there, or what would move there? Or is it the quantum platform cloud, for example, or the cloud API?
Yeah, so I think for sure it would be IBM Quantum Platform and IonQ's Cloud API, and then Quantinuum's Nexus. That's all the ones I can speak to. Unfortunately, I'm not quite as familiar with PennyLane or Catalyst, but or if the AWS SDK has like a more internal runtime side of it as well. I'm not sure if it's a purely managed thing, but yeah, that's basically, at least those would be kind of like my proposal for that separation. And then we can have the same amount of columns we have right now if we plan to get rid of the FTQC one, so keep the table balanced.
Any other thoughts on that? Okay, I guess we can take a crack at creating one and see what it looks like. Did somebody want to say something? Okay, that's pretty much all I had. Any questions about or any concerns? I'm sorry if not everybody has access to the paper. We're just trying to polish it right now. So we're just trying to keep the editing to the like minimal.
In terms of like system requirements, have you like considered adding to the architecture some parts of storage or monitoring?
So we do have this quantum telemetry collection, which collects, and then we have the data persistence service down here, which does what I think you're thinking about, right?
Yeah, I was thinking about more like a visualization dashboard thing, which would have both classical and quantum telemetry, and also like a storage option, maybe like an Apache thing, or maybe a simple Postgres database, which would store some of the information or like our data models.
Fair. I think just so that we don't call out specific technologies, we have that data persistence service, which can be the ones that you mentioned. And for the visualization, you're talking about visualization of the system, so that could like get wrapped into the quantum telemetry collection / visualization. Would that satisfy what you're thinking?
Maybe quantum / classical telemetry collection would satisfy.
Okay. That's a good idea, actually. Like not separate both.
Yeah. And do we want to mention something about like GPUs and TPU compatibilities?
Can you expand on that? What do you mean?
Like so specifically with Slurm, like we will be using GPU and then that can be counted both in not really only on the classical side of telemetry, but there will be some services which will be responsible for the resource estimation part of it. So there, like in the future, we could also think about other devices like DPUs. So if we want to go in that direction. Does that make sense?
I'm trying to wrap my head around it. So when you say resource estimation, do you mean just classical resource estimation, or are you referring to quantum resource estimation?
So for classical, it is quite feasible, but for quantum, we can definitely like think about it. It's like a novel thing. So in terms of resource estimation, what I'm trying to say is that we have all our CPU metrics, time allocation, those kind of things, and then we can consider what all GPU is being consumed, and then there would be service handlers like from Slurm. There will be some consumption or like the nodes which are specifically assigned for GPU tasks. So we will have to maybe capture that somewhere.
I have to grok that a little bit. I have to think about that a little bit, Symmetry. Sorry. Does anybody
Okay.
have any?
I might be able to share some architecture details about that. I'll share that with you in on Slack.
Sure, yeah. And okay. Yeah, we'll chat on Slack. I have an idea, but I'll chat with you separately.
Okay.
Anything else that's missing here, or any concerns that we should address as we move towards April 8th, which is the deadline for this? All right, cool. That's all I had, though. Yeah, the one last thing that I just kind of wanted to mention is as part of the longer journal type of article, we might think about trying to prototype some of these pieces and trying to prove that you can actually couple different stacks together. So that might be one thing that we can consider going down the future as a work item, so that we can put some of these ideas into concrete implementation. Other than that, that's all I had. Is there any other comments, concerns, anything else? All right, cool. Thank you everyone for your time. Appreciate it.
Thanks, Amir. Bye.
Thank you.
Take care. Bye.
Easy.
Thanks, Amir.
Thank you.
Thanks, you.